Good morning or evening or afternoon, everyone, and thank you for joining us. So today we are extremely blessed because we have our speaker coming all the way from New Zealand. And I wish to welcome very warmly Associate Professor Simon Lamb from the Victoria University of Wellington. And also because he's an expert in plate boundaries, which was the main topic of our series this year. And so, yeah, a warm thank you, Simon, and the floor is yours.
Thank you, Catherine. Well, it's a pleasure to speak to such a wide international audience. And I feel a slightly strange feeling to be sitting in Wellington, New Zealand, and talking to people on the other side of the world. Anyhow, following what Catherine asked me to do, what I'm going to do in this talk is really ask the question, which you'll see on the slide here: how strong are plate boundary zones? What sort of level of stress do you need to drive faults and cause all the deformation that occurs between the tectonic plates? This slide, for anybody who's interested, is actually an aerial photograph of one of the ruptures drawing the 2010 Christchurch earthquake. And it's a beautiful example. It's actually a strike-slip fault, but it shows these wonderful radial shears where it crosses flat farmland. And I was saying to Catherine that often with these faults, when you have a surface break, the only way you can actually work out from looking at in the field what's gone on is where you see an offset of a man-made feature, because nature tends not to provide straight lines, and so it's often more cryptic with natural features. Right. So when you look at earthquakes, then it's, almost all earthquakes are associated with the boundaries of the tectonic plates. And that's basically actually how the plates are defined by, you can map out the plates by looking at where the earthquakes are. And it was really the development of the worldwide seismic network in the 1960s that suddenly produced enough earthquake detections that you could start to see this pattern. So this is a map of seismicity between 1963 and 1998, 358,000 events, and you can see just the density of earthquakes along the plate boundaries, including the East African Rift System. And if you go right to the edge of the map, this is New Zealand here. And if we just home in on the Pacific region, the Pacific Rim region is actually one of the areas where you get most of the really big earthquakes on the planet, because you've got subduction zones going all around the Pacific, and they're the ones that generate the really big high magnitude 9+ earthquakes. And this is just a magnitude greater than 6.5 since 2000. So, and this diagram, I think I made it probably about 3 years ago. So this is about 20 years of magnitude 6.5. And you see again how they just define the edge of the plate, though some of the deeper ones will be in the Benioff zone of the down dipping plate. Why is that not? So the question I want to ask, which I sort of said already, is what are the magnitudes of the stresses that are driving deformation at plate boundaries and basically causing the earthquakes? So the earthquakes are really a result of sudden breaking of rocks along faults, and that's what gives rise to the earthquake. So if you want to really understand earthquakes, you really need to know something about the stresses that are actually driving the earthquake activity. why this thing doesn't. Okay, I'll do it. And if you think of an earthquake, it's one way of thinking about earthquakes is they're part of a stress-strain cycle. So you have the earthquake, but between earthquakes, if you're looking at, say, an individual fault, there's a long period where basically nothing is happening. And during that period, the stresses in the system are increasing. So you're getting what I call the stress loading part of the earthquake cycle. And the stresses are building up until they reach the strength of the fault. And at that point, the fault can't support any more stress and it breaks. And that breakage is what gives rise to the earthquake. And you get slip on the fault. And that slip actually takes elastic stress out of the system. And so it relieves the stress. And then you start the next earthquake cycle. I mean, in detail, what tends to happen is that immediately after an earthquake, you get a sort of post-seismic period where you actually get a local redistribution of stress strain. So if you're actually looking right at the fault, generally speaking, there is an increase, the stress actually increases quite rapidly. And then you go into the long loading phase of the interseismic period, building up to the next. If you're slightly away from the fault, you actually get further relaxation of the system. So the stress drop is continuing. So one thing that interested me, I was thinking about this a few years ago, was can you use stress measurements? If you could find some way of measuring the stress in a plate boundary zone, would that be a way of working out where you are in the earthquake cycle? And potentially, would that be a way of sort of forecasting earthquakes? You know, if you were early in the cycle or late in the cycle. So you have a sort of different, if you could sort of image a plate boundary in terms of the level of stress in it, then that might be another approach to forecasting earthquakes. So if you could find really highly stressed parts of the plate boundary, then you'd be worried about those because, you know, like an engineer looking at a structure, if you find a really high stress part, those are the bits that you're going to worry about because they're the bits that might fail. The problem is, how do you actually go about measuring the stress? And so that is really what I want to talk about in this talk. But if we just think about the stress change that takes place during an earthquake, then basically we get slip on the fault. And as I said, that slip is basically transferring elastic strain that's taking place over a wide area into localized deformation on the fault. So you're converting elastic strain into permanent slip on the fault. And so if you think of the system just before the earthquake and then compare it afterwards, what you find is that the elastic stresses round the fault where it slipped have actually been reduced. And this gives rise to what we call a stress drop. But if you look at the ends of the faults where the ruptures terminate, then actually you get a stress increase. So the slip on the fault relieves elastic stress in the vicinity where the fault's slipping, but it actually loads the ends of the faults. And that's probably very important in terms of setting the system up to where it might fail again later on in the system, in the earthquake cycle. And so with some strike slip faults, you get this propagation of earthquakes. So you have slip, and then the next earthquake is the sort of next segment on, but it's been loaded at its end by the previous earthquake. And you can calculate these stress drops, and they're called static stress drops, but just from the slip on the fault. So if you use techniques to work out what the slip on the fault is, you can use seismic techniques or geodetic techniques if you've got GPS network in the vicinity of the fault, and then you can convert that slip using the sort of physics of elasticity into a stress change that would have occurred on the fault. So this is an example of the 2015 Gorkha earthquake in Nepal, which was a thrust earthquake in the, for those of you who are not familiar with Nepal, you're in the Himalayan thrust belt, and it's relieving stress associated with the Indian Eurasian collision zone. And you can see here the pattern of slip. The peak slip was about 6 meters, and this is very typical of earthquakes. You have to imagine the fault plane is quite gently dipping at about 15 degrees. So we're looking at the sort of projection of the fault plane, and then the slip sort of dies away, up dip and down dip, and also a long strike. And if you convert that into a stress change that occurred, you can see that there's a negative means there's a stress drop. So all the area where there was a large amount of slip, you've taken out of the system up to about 8 megapascals. So a typical value would be probably about 4 megapascals. But you can see where the slip is terminating, you actually have this stress loading. So you actually have an increase of stress. So if there's a bit of an argument about how you would what the average stress drop is. But if you average out all of it, you find that the mean stress drop is actually incredibly low for most faults. It's often just a few megapascals. So that's the sort of typical stress change that's taking place during an earthquake. And here's an example of the magnitude 9+ Tohoku earthquake in Japan. And again, you know, this is a big subduction megathrust earthquake. The slip on this earthquake is simply ginormous. So the peak, for those of you, again, not familiar with the Tohoku one, this is northern Honshu. So this is online Japan. And then you've got the trench, the Japan trench here. So you've got the Pacific Ocean sliding underneath this part of Japan. And the peak slip, I think, was up to 70 meters. I mean, it's absolutely phenomenal. And in this region here, but the actual stress changes that took place, and this is probably one of the largest earthquakes instrumentally recorded, is still only of the order. Unfortunately, they've got a different color scheme to the previous slide. So hot colors are now stress drops, where cold colors were in the previous one. But again, the average stress drop is only a few megapascals. So there isn't a relationship between magnitude and stress drop. All magnitude is really telling you the size of the fault plane that's ruptured, whereas the stress drop is really a ratio of slip to dimension. So at the very high magnitude earthquakes will have the same stress drop as at the tiniest earthquake that you can think of. So if we go back to the earthquake stress cycle, the question is, we can measure what the change of stress is during the earthquake, but we can't actually tell from the earthquake what the general level of stress is, which is what I call the background stress. So this is really where the problem is that you can't really use earthquakes to work out the general level of stress. So, I mean, it could be high. So for instance, let's say it could be 100 megapascals, in which case the earthquake cycle would be just really small perturbations on this very high stress level. Or it could be very low, in which case the earthquake cycle is taking everything out of the system and then building it up and then taking everything out again. And you can't tell. So that's really the question is, how would you work out what that background stress is? Because it's the background stress that actually drives the faults. The earthquake cycle is the perturbation on top of this background stress, and it's what that level is that one really wants to know. So the one way of getting at this is to recognize that part of the stress in the system in rocks is related to gravity. So all of the Earth is subjected to gravity. And if you have variations in topography or variations in rock density, then the pull of gravity varies from place to place. And that actually sets up a stress field. And that stress field is always there. Earthquakes have almost zilch effect on that because they're not, a single earthquake's not going to change the overall topography very much. And then you've got what we call the tectonic stresses, which are those imposed basically by the plates. So the relative movement of the plates is imposing a tectonic stress on a system that has this inbuilt gravitational stress. So the total stress field is a combination of the two. And the key here is to see, really, does topography play a significant role in controlling deformation? In other words, can you see changes in the pattern or style of deformation which you can link to topography? Because if you can, what that's telling you is that the gravitational stresses are sufficiently high that they're a significant proportion of the total stress. So they're actually playing a role now in driving the deformation. And just as a basic rule of thumb, if you find that topography plays a strong role, then what it's really telling you is that the overall level of stress isn't very high because the gravitational stresses are not that big. So if you can see a strong role of gravity, you're really talking about total stresses somewhere in the range of 0 to 30 megapascals. So say about 15 megapascals. So in other words, in that diagram that I showed before, it would be the low, the blue system, the low level of stress. So one place to think about this, or at least where I thought about it, was in the Andes on the western side of South America, because this is a subduction zone, so it's a nice plate boundary, but it's also a region with very high topography and a lot of variation in topography along the length of it. So if gravity does have a role, you should certainly see it here because you've got really an enormous amount of topography. So in the central Andes, you've got a wide mountain belt which has an average elevation of about 4 kilometers over a width of about, the high bit is over a width of about 300 kilometers, and the total width of the mountain belt's about 700. And if you go south into the southern Andes, then it's a much lower system. So you've got mountains, but they're only up to about 1,000 meters or 1,500 meters. So from what Catherine was telling me, sort of not far off the elevation of Rwanda. But you've got a simple plate system all the way along here with subduction of the Nazca plate beneath the South American plate along the Peru-Chile trench. So just to illustrate that, if I take two profiles, one through the high central Andes and one through the low southern Andes, then you can see that difference in topography. So for instance, in the central Andes, you've got a very deep oceanic trench. So actually what's important is really the height difference. So you've got a difference between about 7 kilometers below sea level and a general elevation of about 4 kilometers above. So 11 kilometers of height difference here. Well, if you go to the southern Andes, you've got the trenches at about 4 kilometers. And as I say, the general level is about 1 kilometer. So you've got only 5 kilometers. So there's a huge difference in topography in these. So it'd be interesting to have a look at that's what when I was thinking about this, I thought this would be an interesting thing to look at to see if you could somehow use this as a calibration for the level of stress. So just to sort of put you in the picture of what these areas are like, I'm just going to quickly take you on a traverse across the central Andes. So this is the forearc of the central Andes in northern Chile, which is the Atacama Desert, which is one of the driest places on Earth. So here you're at an elevation of about 1,000 meters above sea level, and we're looking up towards the slopes, the western side of the Andes. And if you keep going to further east, you've got a big volcanic arc because it's a subduction zone. And these volcanoes rise up typically to elevations of about 6,000 meters, 6,500. So there's roughly about 2-kilometer height difference between the general land level at about 4,000, 4,500 meters and the tops of these volcanoes. And if you keep going, you get this wide, high plateau, the Altiplano, which is at a level of about 4,000 meters. And this is a view looking actually westward towards the volcanic arc. And then if you look in the other direction from the Altiplano eastward, you actually have a sort of the remains of a mountain range on the other side of the Altiplano, which is called the Eastern Cordillera, which has these peaks here, which again rise up to about 6,000 meters high. This is Illimani, and I think that's Mururata. Anyway, they're high peaks. So you're near, these are high parts of the Earth. And here's one, Potosí, which is one of the high ones in the Eastern Cordillera at 6,000 meters. And then if you keep going east, gradually the general level drops off, and you come to the eastern foothills where you have a big active fold and thrust belt. And here you're at an elevation of only a few hundred meters above sea level. These are big rivers draining off the Andes. And if you look in the banks of these rivers, you can, as you move away from the Andes, you can see incipient thrusts, which are just sort of the, if you like, the most eastern edge of the system, which is just beginning to get caught up in this big mountain belt. What's particularly interesting is is to think of a profile along the length of the Andes. So here is a profile going along the length of the high Andes. And if you do that, what I've plotted here, may take a little while to get used to this figure, but this is basically along that profile, and these are degrees of latitude. So we're going from about nearly the equator all the way to 45 degrees south. So it gives you an idea of how long the Andes are. And this is the high, the average maximum height of the Andes. So you can see that you have what we call the central Andes, which runs from roughly about 11 degrees south to about 33 degrees, sorry, 11 degrees north to 30 degrees south. And this is at an elevation that the high bits of it, say about 4,500 meters. And then as you go into the southern Andes, the elevations drop off, and then you get down to 45 degrees south, where you're only at about elevation of about 1 kilometer. So that, if you like, those two profiles that I showed you would have been, one profile here would have been at about 20 degrees south, and the other profile would have been down here at about 40 degrees south. But and then if you look offshore at the trench, you can see that where the Andes are highest, the trench is actually deepest. So that's, and so as you go to the southern Andes, the trench is also getting shallower. So the height contrast is much greater in the central Andes than would be apparent just from looking at the topography above sea level. But what's particularly interesting is if you look at the tectonics of the mountains, what's actually going on, and you can get this from earthquakes or neotectonics, looking at faulting of young Pleistocene sedimentary sequences. What you find is that the high Andes are in what I would call essentially a neutral tectonic state. So it's hovers around. Some parts are very slightly extensional, but the rates of deformation are very, very low. And some parts are very are slightly compressional, and these can change quite rapidly as you go along strike. But the dominant mode is actually strike slip. So what that's really saying is that there's no net in terms of the stress field. There isn't really a net compressional stress, deviatoric stress, or an extensional one. It's sort of, it's from a stress point of view, it's essentially neutral. And so you can see here that you get mixtures of oblique extension with strike slip, or they can be some thrusting here. And it stays the same in its tectonics all the way along the length. So when you get even into the southern Andes, it's still just like that. It's actually strike slip. There's really no evidence for compression or extension. It's just a strike slip system. So that was something that made me think, maybe you could use that in some sort of force balance to calculate what must be the strength of the subduction zone that can support that height of mountains, given that you're basically just supporting the weight of the mountains. You're not actually applying an overall compressional stress, or it's not collapsing. It's sort of more or less at a balance. So if you take a profile across, these are big seismic lines done by a variety of groups across the central Andes at 21 degrees south. You can see very well image the top of the subducted plate, the Nazca plate. So that's the oceanic crust. And then this is the crust and lithosphere of the overlying South American plate. There's the volcanic arc. And basically in the high Andes, you've got crust that's about 65 kilometers thick. And as I say, typical elevations about 4,500 meters. And then it comes all the way down to the trench. So one can simplify that system into what you're really looking at is you've got a wedge of material here that's sitting on the subduction megathrust. And it's got to provide a horizontal force through the megathrust. The stresses on the megathrust have got to exert a force such that you can balance the weight of the high Andes, bearing in mind that it's essentially in a sort of neutral situation. You're not overall compressing the high Andes, or you're not providing insufficient strength and they're collapsing. You're more or less at a balance. So basically, you can think of the weight of the Andes as providing a lateral push, which has got to be balanced by the stress that you apply to the megathrust. And so that's really where the calibration comes in, because one thing we can calculate is what this lateral push would be, because that's actually coming from gravity. So just as an analogy, if you take something like a tank of fluid, then to keep the fluid in the tank, you actually have to provide a force on the size of the tank. Now, if you've got a glass tank, that force is actually provided by the strength of the glass. So the glass in a tank is actually quite stressed because it's got to provide a sufficient force to support that fluid and basically the weight of the fluid. So the effect of gravity is causing a pressure, a horizontal pressure in that fluid, and that's got to be supported by the edge of the tank. So that's sort of the situation that we have in the Andes. The weight of the high Andes has got to be supported by some push that's come from the megathrust. And we can think of what this lateral push is in terms of what we call a buoyancy stress, which is really just the integration of the pressure with depth. So for a tank, then the pressure is just rho GH, the depth of the tank, where rho would be the density of water, or in the earth, the density of rock. So the average stress is would be here half rho GH. And the total force is actually half rho GH squared, because you apply it's the stress times the per unit length is the depth of the tank. In the Earth, it's a little bit more complicated because we're not dealing with a material of a constant density. We've got a crust, a low density crust sitting on top of a higher density mantle. So we have to take that into account. But basically what we can do is integrate the pressure with depth to work out what that buoyancy force is. And then if you divide it by the depth, that actually gives you the buoyancy stress. But in terms of our calculation, we're interested in the force. So it's the integrated pressure with depth is that lateral push that's got to be supported by the megathrust. And if it's not supported, then the Andes will collapse. So if you take, again, a fluid, if you have a mound of fluid, then if there's no support, that mound just flows away. So something's got to keep it up. So you're working against gravity. So if you go to the Andes situation, here we've got this triangle, and we've got the weight of the high Andes, which is exerting a horizontal stress through gravity, and that's got to be balanced by the stress that we're going to apply on this subduction megathrust. So we can calculate what we call a force balance to work it out. So we use basically the gravitational stresses from the weight of the mountains to calculate what the stress must be on that megathrust. So if you do that, what you find is if you go along the length of the Andes, then the general level of stress, average stress on the megathrust, is about 35 megapascals. And in the high Andes, it's actually quite high because you've got such high mountains, but also the trench is very deep. And so it reaches, in this very simple-minded calculation, perhaps 40 megapascals. But as you go down into the southern Andes, the stress becomes very low. It's actually only about 10 megapascals because the tectonics in the Andes is not changing along its length. So that variation in topography actually is reflecting the variation on the stress on the megathrust. And if you look at subduction zones worldwide, what you find is that generally speaking, the elevations of the mountains behind a subduction zone are generally in the range of about 1,000 to 2,500 meters. That's typical heights of the high parts of plate boundaries behind subduction zones. And you can see the central Andes is a complete outlier. You can see it's just in terms of topography, it just dwarfs all other subduction zones. So what this is actually telling you is that for most subduction zones are actually rather like the southern Andes. So the southern Andes is one of these profiles. I can't think which one. So the general level of stress on megathrusts in subduction zones is actually quite low. It's probably only about 15 megapascals, whereas the central Andes is actually a complete outlier and is possibly as high as 40 megapascals. So that would be, I think that the megathrust in the central Andes is probably one of the strongest faults on the planet. And there are special reasons why that's so, which I'll go into. But generally speaking, big faults like megathrusts are actually quite weak things. They're as only 10, somewhere between 10 and 20 megapascals. They're not very strong. So that, going back to that original thing about whether the background stress is high or low, this is really saying it's actually at the low end. We can be a bit more precise about this. You can actually model this system in a more rigorous way by thinking about, for instance, part of the system where the stress transmission is taking place is a brittle system, and that's which is going to fail in these big subduction zone earthquakes. And part of it is ductile deeper down, which will probably result in aseismic slip. So the stress transmission is actually varying along the length, but the integrated force has got to be enough to support the height of the, for many subduction zones, it boils the volcanic arc behind it. But there is especially when you're looking at the ductile part, there's a close relationship between temperature and shear stress. So, for instance, things like the age of the subducted slab will now play a role in what those stresses are. And also the rate of subduction plays a role in terms of shear heating, because you're doing work, and so you'll generate heat. So that will tend to lower the stresses as well. So you can think about the stress transmission in a megathrust as the brittle part, where the stress will be, shear stress on the will be proportional to the normal stress, so basically proportional to depth. And then you reach some peak value, and then as you go deeper, the pressures are much higher, but the temperatures are higher, and you move into the ductile field, and basically the stress drops off as the system gets hotter. So that the stress transmission reaches, it has some maximum value at some, which should probably be the depth at which big megathrust earthquakes nucleate. So probably at depth, typical depths would be about, say, 30 kilometers. And deeper than that, the system becomes ductile and becomes weaker. In terms of the temperature, what tends to happen is that in the brittle part, the temperature gets higher as you go into the brittle ductile transition. And then you get this buffering between, as it gets hotter, it gets weaker. So there's less actual shear heating, and they sort of buffer each other. So you get actually not much, the temperature is relatively constant. And then you get to the bottom of the subduction zone, where it starts to see the corner flow created by the slab penetrating into the mantle. And that actually brings in a large amount of heat, which actually heats up the system, and it comes so hot that basically it terminates the stress transmission. So the stress will look like this, though it may be complicated by, if you've got a moho in there, you might have some move into the mantle, which might still be brittle, but of a different strength. So to actually calculate that, you have to basically calculate the stresses and the temperature jointly. So it's a slightly more elaborate calculation, but they're analytical expressions for what the temperature might be, depending on the heat sources, like this would be from the subducted slab, the shear heating, and whether there's any radioactivity generating heat, and also the rate of subduction actually takes heat down. So what I did was I took a whole bunch of subduction zones around the Pacific region and assumed that the basic fundamental material properties are the same, and see if I could calculate what those properties were by looking at the geometry of the subduction zone and the heights of the mountains behind it. So I have a calibration about what the total integrated force is from this overall force balance. And there's a lot of seismic data about what the geometry of these subduction zones are. So I'm just picking subduction zones where we have a good understanding of what the geometry is. So Cascadia is an example here. So the sort of things that might affect the stresses in the subduction zone would be the age of the subducted plate, because that actually is determining the temperature depending on how much the heat flow coming from the subducted plate, the convergence velocity, because that actually will affect the shear heating. It actually affects the system in two ways. One, in the shear heating, which will tend to raise the temperature, but it's also taking heat out of the system through the subduction as well. So it actually works both ways. So it's slightly complicated. Crustal thickness will probably affect it in terms of the radiogenic heating. composition in terms of just basic strengths of different rheologies, and also the possibility of some lubricant in the system, of which an obvious one would be water, pore fluid pressure, or presence of wet sediment. So what you find is that a typical temperature profile, if you for sort of typical values of all these parameters that satisfies the force balance, would look something like this. So the temperature goes up in the brittle bit, then as I said, you get this buffering bit, and then it goes up very high when it hits the corner flow. And what the stress looks like is the stress goes up in the brittle part, the slight change in because you go from cross to mantle rheology, and then the stress is buffered, and then the stress goes right down to zero once you get into the hot corner flow. And typically speaking, the frictional coefficients are incredibly low. So bearing in mind that the overall shear stresses are very, very low, given that the topographies behind subduction zones aren't very high. So you're talking about effective coefficients of friction of 0.03. So if you think of, a typical friction that one sort of taught about in some undergraduate courses of 0.6, 0.7 for dry rock, that in reality, in the Earth, frictional systems behave as though they've actually got a coefficient of friction which is at least an order of magnitude less than that. And you can explain that by basically very high pore fluid pressure. So the pore fluid pressure is probably greater than 90% lithostatic, which is sort of not surprising because subduction zones are incredibly wet systems, because you're taking all this sediment which is saturated in water down. So you can have different types of subduction zones depending on the age of the subducted slab. So if you take something like Cascadia, which I'd call a hot subduction, because the slab is only about, the oceanic crust only 10 million years old. So what happens that it's very hot, and the incredibly weak. So you can see a peak stress of about 20 megapascals and an average stress on that system of about 10 megapascals. You can take a cool subduction zone like the one in New Zealand, and it's also very weak, perhaps just a little bit stronger. But in cool subduction zones, more of the strength in the mantle, whereas in a hot subduction zone, there's virtually no strength there at all, and it's all in the brittle part. But overall, they're still very weak, and they still require these very high pore fluid pressures here, about 94%, with these effective coefficients of friction that are incredibly low. But if you go to the central Andes, where you've got this very high range, this is a sort of outlier where you've now got coefficient of friction of nearly 0.1. So this, as I say, this is unusually high, with a lot of strength in the mantle part, and still incredibly wet. I mean, you've got a pore fluid pressure of about 80% lithostatic. So it's not as though these are dry systems, they're all wet. It's just that this is a little bit stronger, probably about 3 times as strong as a typical subduction zone. And that's why you can get these very high mountains. And you can, that's consistent with the heat flow as well. If you look at the heat flow in northern Chile, it's consistent with this higher strength. So just to summarize, if you looking at subduction zones around the planet, most subduction zones, the megathrust it has a strength somewhere between 7 and 15 megapascals, so typical about 10 megapascals. If you look at big thrusts on the edges of mountain belts, these aren't subduction megathrusts, but big fold and thrust systems, then you can do the same game, and you find the strength of it is again very weak, about 15 megapascals in the Andes. If you go on the eastern side of the Andes, about 13. In New Zealand, some of the big faults there, about 12. So that's the typical strength of faults in the crust, the average strength of it. And as I say, in the northern Chile, which is this outlier, perhaps nearly as high as 40 megapascals. But most plate boundaries, these are the levels of stress that you're dealing with. I was talking about this difference between, why is there this difference between the southern and central Andes? Well, I think that there's a very simple explanation for that, is that the central Andes is essentially the driest system we have. It's still very wet, but it's drier than other systems. And the reason for that is there's basically no sediment in the trench. So it's the sediment in the trench is the way the water gets into the subduction zone to provide this lubrication. And it's a climatic effect, because the Atacama Desert is incredibly dry, mainly due to the rain shadow effect, but also due to the fact that you've got these cold currents, the Humboldt current, coming up, which basically suppresses evaporation from the ocean to provide moisture. And so there's no sediment coming into the trench at all. So the trench is actually bare ocean crust. So it's very, very rough, with only a very thin veneer of pelagic sediment on it. And that basically is poorly lubricated and empty trench. And that allows you to get these slightly higher strengths up to about 40 megapascals. Where the southern Andes, the trench is absolutely full of sediment, because it's all glaciated regions. There's it's a wet climate, very wet climate, a lot of rivers draining into the forearc, and that's incredibly well lubricated, and sediment just gets dragged all the way down the system, wet, sloppy sediment, high pore fluid pressures, and so it keeps the shear stresses low. And this system is actually, the lubricated one is typical of almost all subduction zones are like that. And you can see this transition between lubrication and taking away the lubrication. It all takes place here at about 33 degrees south. And do you see how suddenly the Andes start to get high? So here you've got the high, 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 and then suddenly, you know, you're into the low Andes, and it's just at this point here. And if we look at what's going on in the trench, this is this region here, just to the south, do you see how the trench is absolutely smooth? It's just full of sediment. We just go a little bit north, and it's just bare ocean basement going in. So this is a very abrupt, and here's a nice example. These are these multi-beam images done by a German group. You can see that there's the sediment, just flooded with sediment. The trench is hardly there. You can hardly see the trench. And then suddenly it all stops, and look at it. You can see the actual topography of the faults from the mid-ocean ridge going in this very, very rough basement. And it's that, there's almost like a step change in strength of the megathrust. And the mountains just show that, express that in there. The mountains suddenly can rise much higher. There's more force available to push them up. So just to summarize that, so going back to that initial diagram of the average shear stresses, if you look at the color scheme here, then green is where basically the trench is empty. And then white is where it's full of sediment. And then this sort of pale green is this sort of transition period where there is roughly about half a kilometer of sediment. And that turns out in the Andean system to be the sort of critical amount of sediment. And the reason for that is that the basic basement topography in ocean crust is about 500 meters. So that actually is just reflecting the original normal faulting at the mid-ocean ridge. And if you've got less than 500 meters of sediment fill, you're not smoothing out that topography. And so you've got these rough, strong bits of basaltic crust going down into the subduction zone, and they're capable of transmitting significant stress. If you fill up the whole system, then basically what happens is the megathrust becomes very, very smooth, and it just decoals on wet sediment, and then you get this big drop in strength. So basically low shear stress, thick trench fill, high shear stress, empty trench. Okay, so that's a particular type of fault. These are the big faults. But what about the, you know, the general level of the deforming crust? Well, you can do the same thing, but in a sort of slightly more slightly different approach. I've done this for New Zealand. People, this has been done actually in other plate boundaries as well by other groups. But if we take New Zealand, we've got, you know, a pattern of active faulting, sort of average slip rates on individual faults somewhere between 1 and 30 millimeters a year. And they're accommodating the oblique convergence of the Pacific and the Australian plate. And we can convert that into a velocity field by basically looking at the slip rates and smoothing that out. So we can produce what I call a quaternary velocity field. So this is a velocity field average over tens of thousands of years. So this is the velocity field that would apply. You've averaged out the seismic cycle. We're not talking about the seismic cycle now. We're looking at the long-term velocity field calculated from the geological slip data, fault slip data. The other thing that we can look at is the style of deformation. So basically what we're doing is we're looking at the orientation of the stress tensor. So what's the direction of the maximum horizontal principal axis stress direction? And basically you can do that from looking at things like earthquakes, give you an idea of the fault plane solutions. You can get an idea of the orientation of the stress tensor, or you can, if you look at use GPS, if you assume it's isotropic, then you can assume the stress tensor is parallel to the strain rate tensor, and do that as well. You get a sort of relatively good fit. So what we've done is we've used actually that velocity field and got the strain rate tensor from the velocity field, and then use that, assume that that has the same shape as the stress tensor. So this is the direction of the maximum principal stress direction, horizontal principal stress direction. And you can see that it's fairly uniform across New Zealand, but here you've got back arc spreading, so it flips around by about 90 degrees. And then we can also work out the stresses due to gravity. So what we're doing now is we're looking at the topography and the density structure of the lithosphere and work out the buoyancy stresses related to that. And you can then convert that actually into a stress field. So there will be a stress field just related to gravity because of this variation in the weight of the rocks. So what we're doing really is we're saying, what would the tectonic stresses that applied to the plate boundary need to be in addition to the gravitational stress field, which we can calculate, to give us an overall stress tensor which has the same shape that we've calculated from fault plane solutions or the long-term velocity field. So we're just basically saying that we're using gravity as a calibration to work out the magnitude of the stress tensor, given that we know the shape of it, the orientation of it. And if you do that, basically to do that, you use the, have to have some sort of simplified model. So if you assume that the deforming zone is a sort of thin sheet, viscously deforming sheet, then you can use the governing equations of viscous flow, which is basically that the horizontal gradients of shear stress are balanced against the horizontal gradients of buoyancy stress. So those are just, that's just the mathematical formulation of what I've said in words. And if you do that, you can then calculate the stress field. the full stress field in the plate boundary. And what you find is, surprise, surprise, it's very low. So it's exactly the sort of stresses that you would have calculated from these force balances on the megathrust, that are typical values are about 15 megapascals. So the system is actually very weak, which is exactly what we would have predicted from the heights of the mountains, the strength of the megathrusts. But we get a slightly better spatial resolution of this. And going back to my original point is, could you use this to say something about forecasting earthquakes? Well, if you could improve the spatial resolution of this, then, and you could use fold-in GPS measurements, which are giving you the instantaneous stress shape of the strain rate tensor, which you might relate to the stress tensor. Potentially there's a way in there, but there are all sorts of problems with it. But to go back to this original thing about the earthquake stress cycle, is the background stress high or low? The answer is that it's low. And typical ranges of the stress levels in a plate boundary zone is in the region 0 to 30 megapascals. So a typical 15 megapascals would be a sort of mid-range value. And so the seismic cycle is basically going from taking a big earthquake, takes almost all the stress out of the system. And sometimes it takes so much stress out of the system that you can actually get collapse, which is possibly what happened in the Tohoku earthquake, where the whole of Japan, parts of the stress tensor flip round by 90 degrees, and you got a lot of normal faulting taking place immediately after the earthquake. So the onshore Japan actually started to collapse after that earthquake because you'd taken so much stress out of it, all the support had gone. And then through the cycle, that stress will build up again and it will go back into compression. Once you have the stresses and you know the strain rates, then you can, if you're approximating the system as a viscous system, you can work out the effective viscosity, which, if you like, is a measure of the strength. And so what you find in New Zealand is that the plate boundary zone is essentially a weak channel, which is has a typical viscosity of about 10 to the 21 Pascal seconds. So that's a typical sort of measure of strength, if you like, of the lithosphere. And people have done similar calculations for Western North America, the San Andreas system. You can do it in the Alpine Himalayan zone. And those are the sorts of viscosities that you get out of it. So again, all that's saying is that given the strain rates, there are the stresses can't be that high, or put it the other way around. Given the low strain rates, given the low stresses and the strain rates, the system has to be pretty weak. So that's probably the sort of conclusion of what I have to say, is that plate boundaries are very weak in the, you know, if they're only a few, you know, 10, somewhere between 10 and 20 megapascals, and slightly larger than the typical stress drop of an earthquake, but sort of comparable to it. So if you think about that in terms of our sort of basic understanding of faults, I mean, it's commonly thought that, you know, and if you drill into rocks, certainly top few kilometers, that the pore fluid pressures that prevail are hydrostatic. In other words, all the fractures are connected and they're just feeling the weight of the water. So you have this hydrostatic conditions. And if the conditions are hydrostatic, then you'd expect the rocks to be a lot stronger than you actually observe. There would be possibly an order of magnitude, at least an order of magnitude stronger. So if you take a sort of strength on a sort of typical fault, then under hydrostatic conditions, assuming a typical dry coefficient of friction, so Barley value of about 0.6, that basically when you got down to about the base of the seismogenic zone at about 15 kilometers, you're talking about strengths on that fault to get, or stresses needed to get that fault to move, of about 150 megapascals. So an order of magnitude higher than the bulk strength that plate boundary zones actually look like when you observe them. And to get those strengths that you actually observe, you need basically near lithostatic poured fluid pressures. So how do you sort of reconcile these two things? Because, you know, when you drill, it looks like it's hydrostatic, and yet when you look at the bulk behavior of the system, it looks like it's near lithostatic. Well, one suggestion that I have is that there might be two systems of fractures. So you have a connected system of fractures, which is actually hydrostatic, and that's actually very, very strong. So funnily enough, those fractures are making the crust strong. So that's not where it's going to fail. It's not going to fail on those fractures because the stresses are not high enough to get it to fail. But you also have a whole system of fractures which aren't connected, which are at near lithostatic, and that's where it does fail. And that's probably what in my view anyhow, that's what microseismicity is. Microseismicity is basically near lithostatic fractures failing, and they fail all the time. You know, if you do look at plate boundaries and you look at the seismicity, it's just an absolute storm of microseismicity. So it's cracking away all the time. And these must be these not disconnected fractures, which are at very high pore fluid pressures. And then you have systems where those disconnected fractures are organized into fault zones, and those are the actual those are the systems which will fail as big faults every so often, every few hundred years or so. And what must happen then is that one of these fractures in the big fault goes, and then it actually then creates this very high stress concentration at the ends, which then can propagate to link up with another one. And then gradually, if you can get enough to link up, you can actually get the whole system to fail. So it basically fails at its weakest point, and you've got to get a system where you can actually get these cracks to propagate to get to the next high pore fluid pressure part. Or it may be that just you only need one of them, a sufficiently large isolated fracture at high pore fluid pressure to go, and then that can actually keep propagating. Certainly if you have, for instance, velocity weakening, so if you have some system where as it slips, the thing actually weakens just through the slip, this is this rate and state friction, and then that system can propagate. So the trigger is the failure of one of these high pore fluid pressure bits, which is why the system looks weak, because that's when it fails. Whereas the hydrostatic part is actually providing a strong framework, which rarely fails. Because if that was the strength controlling part, then you basically wouldn't see the impact of topography on deformation. The system would just be far too strong. Topographic induced stresses would not be enough. Okay, well, I've probably gone on much too long, so that's the end of my talk. So just as a summary, so big megathrusts, so these are the biggest faults on the planet, are very weak faults with typical stresses at failure about 15 megapascals. the average deviatoric stresses in a plate boundary somewhere between 0 and 30 megapascals, so quite low. Typical bulk viscosities of a plate boundary would be about 10 to the 21 Pascal seconds. And these low strengths must be because of very high pore fluid pressures. But also you could have, for instance, weak minerals in the system as well, which have much lower coefficients of friction than you would predict from a simple sort of Barley relationship. So it's a combination of those two that is making the system very weak. Okay, that's all I have to say.
Well, thank you very much, Simon. That was an excellent talk, brilliant talk. We have the time for questions. So either you put your question in the chat and I'll read them on your behalf, or you can unmute yourself and talk to Simon directly. Michael, yeah, please go ahead.
Yes, thank you for this really nice talk. Can you hear me?
Yes, I can. Yeah.
Thank you. So you are mentioning on this conclusion side that the average shear stress is about generally around 15 megapascal or less, or the deviatoric stress in plate boundary range between 0 and 30 megapascal. But and you often use the mean to compare those different plate boundaries. But wouldn't it makes more sense to use maybe taking into account like as you have shown in the previous slide, that the strength profile is the strength at plate boundary is much higher at close to the brittle ductile transition. So wouldn't it make more sense to look at the maximum shear stress instead of looking at the average? Because then we would see much more variation in. I mean, we would consider much more variation between different subduction system and the way the stress is transmitted through the subducting plate to the overriding plate. Or
yeah, I mean,
yeah.
So
my question is, why not using the maximum?
Well, I suppose it sort of depends what the way you're looking at the system. I mean, if you're looking at the sort of bulk behavior, so for instance, in these thin sheet models where you're basically looking at the average strength of the system and the average stresses, then that would be the value. But you're quite right. I mean, when I started that analysis on the megathrusts, it was a very simple-minded analysis. So I was just looking at the average shear stress. But when I then did that more refined analysis, you're quite right that in fact, the peak stress at the base of the brittle system, like for instance, in the central Andes, the peak strength of the system is about 100 megapascals. So it's going from 0 down to about 100, and then it moves into the ductile bit, and then it drops off. So you're probably right that by saying just an average, it's sort of glossing over that parts of the system can be much stronger. And the same would apply in New Zealand. When you look at it in a bulk sense, it has this very low strength. But if you went to the base of the seismogenic dome, it would be higher. Yeah, I mean, I suppose it's just sort of what particular aspect of it you're interested in. And I suppose I've been looking at it in a very sort of averaged way, but it's still following the basic principles of brittle deformation, that it's, as you increase if it's brittle, it's frictional. So as you increase the normal stress, it's getting stronger. And I suppose it would be interesting, that's another thing, is to say what the maximum strength of the system is. But there's a big argument about how you relate that sort of how you reckon. I mean, my interpretation of trying to reconcile low strength with this sort of idea of high pore fluid pressure. I don't think, you know, a lot of people wouldn't accept that and say that what's happening is that you've got the strong part of the system, which is the bit that is hydrostatic, is just very thin. So you've got, you know, if you're looking at 100-kilometer thick lithosphere, then maybe, you know, if you've got a top 15 kilometers, which is hydrostatic, by the time you've averaged that over the whole thickness of the lithosphere, you've sort of lost that element of it. I had a student, and we looked at that, and we tried to basically the calibration then comes down to when you work out the effect of topography over what depth do you go down to. And we tried, and there's been a number of papers that have done the same thing, where you basically rather than going down to a depth of 100 kilometers, you say, well, I'm going to assume that all the strength is in the top, say, 20 kilometers, and you still actually get quite low strength. So I think that my feeling is that it's difficult to explain it, to say, well, it's just that the top part is hydrostatic, but it's not very thick. It's difficult to make that work, but some people do argue for that. So it's a good point. I agree with you.
Thank you very much, Michael.
Thank you.
Karim?
Thank you very much. That was really, really inspiring. And myself, I remember your paper that was published in EPSL in the late 80s about block rotation in a plate boundary. That was really a landmark paper for me. I mean, I remember that paper many years ago. So thanks for this contribution.
Well, you're probably the only person who's read it.
No, I don't think. I mean, it has been cited by more than 200 people, I think. So anyway, that was really interesting. I have just few comments. I mean, very simple ones. I mean, what is the take-home message in terms of seismic hazard out of what you are talking about? I've been consuming a little bit the work of Kellyn Wong in different regions, in which he was identifying 3 different time scales. I mean, let's put it this way. I mean, the post-seismic, in which the after-slip might be important, and also the interseismic 1 and the interseismic 2, comparing all these different big subduction machines and so on and so forth. And here you're bringing something that is quite interesting also within maybe fast deforming regions, on the importance of looking at stresses that are more external forces plus body forces within the system. And I would like also to hear an extra comment on what you think and how would this work specifically in low deforming regions. I don't know whether you've seen the Moroccan earthquake that we had recently within an intracontinental mountain range, in which the basic thinking now is that maybe the external forces are not contributing very much to the system, but maybe the other parts of the stresses are. So this has implications on basically defining maybe really a new way of looking at earthquake hazard, in which we're just used to look at earthquake hazard in places where external forces are important.
Yeah.
Thank you so much. Thanks. That was nice.
No, I think that's very interesting. I mean, I think that people often, you know, underappreciate the role of gravity. I mean, another area where it's quite interesting in this, I don't know much about the Moroccan earthquake, but if you go to the San Andreas fault, was very surprising about the San Andreas fault is that you've got this big strike slip fault, and in the section north of the bend where it's creeping, and it's, you know, it's a sort of almost like a sort of classic vertical strike slip fault creeping away. But all the recent historical earthquakes have been thrust faults either side of it. And it was, you know, like there was the Coalinga one, the Kettleman Hills one, the San Simeon earthquake. And everybody was completely taken by surprise, because they think, why on earth are we getting thrust faults, earthquake thrust faults, in a situation where what's actually dominating the system is pure strike slip that's creeping. Where are these thrusts coming from? But what's quite interesting is if you look at what the way it's working is that you get this coastal ranges, and the strike slip is going right, is actually at the highest elevation of the system. So the San Andreas is creeping right on the tops of this range, whereas to either side, it's actually got the thrust faults. But if you look at the overall plate convergence, it's pure strike slip. And so I think that must be a gravitationally induced thing, that I think what's happening is that the range is actually collapsing at its side. So it's definitely the other example is in northern Chile. I showed that slide of the Atacama fault, which is a normal fault. And then you think, what on earth is this normal fault doing at low elevation in in a highly compressional system that is holding up mountains that are 4,000 meters high? And it's a sort of, you think, what's that fault doing there? Because, and that again, what that probably is, I'm convinced now, is it's a bit like the normal faulting after the Tohoku earthquakes, that you get these, after one of these really big earthquakes, you have so much stress taken out of the system that the whole forearc just literally falls into the trench, and you get this normal faulting, but it only takes place immediately after one of these big thrust systems. So it's not actually telling you anything about the regional stress field. It's just a gravitational effect. So yeah, no, I think that they're thinking of earthquakes always in terms of some regional stress field, which sort of ignores the effect of gravity locally. Sometimes you can miss. It's difficult to understand sometimes what's going on.
Yeah, thank you so much. Thanks.
Okay, Hamea Mulune.
Okay. Thank you so much. It's really sad. I couldn't join your talk since the beginning. I joined only the last part of it. I came from Ethiopia, so I work on the main Ethiopian rift. And one of the things we see in that region is that when there is a magmatism, when this magma solidifies, it really affects the strength of the crust and the faults in general. Have you specifically looked into this kind of behavior, how when the melt solidified affects the strength of the faults, how it affects the strength of the plate boundary?
I've never looked. Well, I have to. The short is no, I haven't. We do have in New Zealand a back arc region, which is called the Taupo volcanic zone, which is actually also incredibly magmatically active. You've got the enormous amounts of melt being produced there. And you can get, I don't know about the affecting the strength of it, but the whole process of magmatism, of bringing magma into the system, actually causes flexure of the crust, which actually can create a lot of faulting, which again, following on from the previous point, is difficult to understand if you're just trying to understand faulting in terms of a regional stress field. That you basically you're creating stresses related to the magmatism, which can give you rather odd results. Like, for instance, I actually wrote a paper on this a few years back, where in the central part, and in fact, I would be very interested to know whether you observe a similar thing in the Ethiopian system or in the ICTP region, is in the central part of the rift of the back arc rifting thing in New Zealand. It's actually under compression. And it's a sort of, you think, what, again, it was like, what on earth is the center of a rift doing under compression. It doesn't make any sense at all. But what it is that the due to the magmatic process, the whole center of the rift is being pulled downwards. And so it's basically, as it gets pulled downwards, it's, if you like, a fold. It's coming like that, and it's actually compressing in the middle. And you can see that in the geodesy. The GPS actually shows that the middle of the rift is shortening. It's not extending. But it can't be a long-term effect. It's a short-term related to the magmatic processes. But in the long term, it averages out as extension. So I think you get local thrust faults in the middle of the rift. But as I say, that would be there'd be short periods when this happened, but there would be much longer periods when it's rifting. And I've looked at some of the GPS in the ICTP-EAIFR region, and there is a suggestion that you see the same thing there, that you get their sort of local areas of compression in the middle of the rift, which again, you can't, difficult to understand if you're just trying to think of a regional stress field of rifting. You know, it's a sort of local thing, process, which is adding stresses to the system in the short term.
Okay, thank you.
Any other question? We had actually someone in the chat, Eleonora Rivalta, saying many thanks for the very interesting and inspiring talk.
Oh, thank you. Well, the PAR remained on here. I don't know if you, those who are still here, I was telling Catherine that we're in the middle of a very violent storm in New Zealand. A big southerly is blowing through. So I was worried that the PAR would go off, but it stayed with us.
Yes, and we have another comment from Charles Forrester. Thank you very much. Really enjoyed it. Got to go. So maybe we'll end it there. And yeah, I had exactly the same comment, Simon. It was an excellent talk, and I thank you very, very much.
Well, thank you for inviting me, and thank you all for logging in to listen to it.
Yes, thank you to the audience, because today we had many people, and thank you very much for joining us. Thank you.
Thanks, Simon. Thanks.
Great. Okay, then I'll say goodbye to everybody then. So,
Yes.
Catherine, I just stopped the share, do I? Like that?
Yes, yes.
Okay,
All
now
good.
I get a feel for the audience.
Ciao.
Okay, bye everybody.
Bye.
Bye.
Bye.